All right, and just a reminder, as you're looking for 4 different groups. So what we're gonna do is we're gonna go through these, and we are just going to see which ones meet that definition, okay? So for A, are there any? Are there any chiral centers? All right, very good. Exactly. So there's no placement in which there are 4 different groups. For B, what you guys get? None. Very good. Way to identify that the fact that just because it the ring kind of looks like it could be a few different groups, it's not. C. Okay. Very good. D. E. Okay. F. All right. Finally, some controversy. Okay. So let's start top left corner, okay? I'm going to box the carbon that we are looking at to determine whether or not it is a chiral center. Okay. If you follow this path in red, okay, tell me whether or not it differs from the path in green. Does it? Hmm. They're the same group. It's not a chiral center. Okay. All right. We're going to do the same thing in the other corner. Okay. So, and then up. Red. D had 2. Yeah. So A, none. B, none. C, none. D, 2. E, for our purposes, we're going to say 0. And then for F, it's also 0. Okay. Can you explain D? Yes, I can. So let's look here and here. Okay. How many groups are there on the one? How many different groups are there to the one to the left, right? I have the methyl. I have a hydrogen. Okay, so methyl, hydrogen. I have this set of carbons. I have that set of carbons. That's 4. Okay. Does that make sense? Okay. Keep in mind, it doesn't only matter about the atoms directly connected to the chiral center. It matters about the whole group that's connected to the chiral center. Okay. Okay. Great job. No, I wanted to continue to. All right. Next. Yeah. I don't think you guys really need to worry too much about this. We actually have another section where we're kind of going to go way more in depth with this, okay? But for now, I'll just talk about it. Basically, what is chirality? Chirality means that something has a non-superimposable mirror image, which is a fancy way of saying that it has an enantiomer, okay? Me personally, I could never understand the definitions from this chapter. The way that they explain like the mirror and the hands, like I've sat in lecture like what 4 times now, and I still don't get it. So basically for you, if you get it, that's awesome. If you don't, I literally just want you knowing that chirality means that something has an enantiomer. Okay. And that's way easier to determine. Okay. So basically what I have going on here is actually more of a test for meso compounds than it is really for chirality. But we'll get into that later. But for now, I just kind of want to skip it. Okay. This is probably the most important thing from this chapter. Okay. So when you're naming RNS, the very first thing that you look at are the atoms that immediately surround the chiral center. Okay. And remember, whenever you're doing S and R, it needs to be a chiral center, or else you're not going to get an answer. Okay. Okay. So, basically the first step is just to look at the immediate atoms, and then you just rank them in terms of atomic number. Okay. So if I have like an oxygen, a nitrogen, a carbon, and a hydrogen connected to a chiral center, then I'm going to rank the oxygen first because it has the highest atomic number, then nitrogen, then the carbon, then the hydrogen. Okay. Okay. If there's a tie, you're going to look for the highest atomic mass. Okay. That's really only ever useful if there's like a deuterium or something on it. Okay. But if we do have a tie, say we have like 2 or 3 carbons around a chiral center, which is very, very, very common, especially in organic molecules because they're just made of carbon. Basically, you need to look at those carbons that are immediately connected and then ask, okay, what's coming off of them, right? Well, we're going to look at for examples later, but you're going to want to list them, okay, going from highest atomic number to lowest, and then you can compare the 2 carbons that you're looking at, okay? When you're doing that process of listing out the atoms, if something has a double bond to, like, say we have a carbon double bound to an oxygen, we count that as 2 bonds to oxygen, okay? Always keep that in mind. When you've given priority to everything, you want to connect them 1 to 2, 2 to 3, and then 3 to 1. You do not include 4 within that circle, okay? Okay. If you get clockwise, it's R. If it's counterclockwise, it's S. But it only ever works if 4 is in the back, okay? If 4 is in the front, you just immediately flip whatever you got. You don't need to do any tricks. You don't need to do that little switch method you might have learned in class. Just immediately, I really want you guys just focusing on the fact that if you got S, you put R as your answer, okay? Make sense? Okay. If the H is on the plane of the molecule, okay, so if it's on a straight line, that is when I want you guys using the method you learned in class, okay? And I should have an example in here that I can kind of teach you guys how that works, okay? One final note in RNS, if you have 1 stereogenic center or 1 chiral center, then you just put S or R in parentheses dash rest of the name, okay? If there are 2 or more, then you need to number them, okay? When you're ordering them, okay, you are ordering them in numeric order. you're not trying to alphabetize S versus R, okay? Don't overcomplicate it. Make sense? Whack, I don't have practice on that. Okay. Got it. I know what I do. All right. So we're going to table that R and S for right now because we apply it to so many different things throughout this chapter. Because kind of the way that I went through this class was just trying to find problem solving strategies that worked for me. And for this chapter, kind of all of those strategies just came back to identifying R versus S. All right. And so you guys will get a lot of practice with R and S as we go through and solving some of the applied problems. Okay. So determining relationships. This kind of question is likely going to come up as like, which of the following are constitutional isomers? Are they diastereomers and enantiomers? Are they identical? Are they neither and just completely different, right? Are they meso compounds? These sort of things are going to help you answer those types of questions, okay? So the first step, finding the molecular formula, okay? If they are different, then they're just completely different molecules and you don't need to go any further, okay? If they're the same, you're going to ask, is the connectivity the same, right? If I have this structure, right, and also this structure, they're going to be constitutional isomers because the connectivity is different, right? We have a 1,4-methyl and then a 1,3-methyl, right? They're just going to be different. They're going to be constitutional isomers, okay? Right. If the connectivity is the same, you're just going to move on. After that, what you're going to do is you're going to count the stereogenic centers, okay? If it's 0, then they have the same molecular mass, molecular formula, the same connectivity, and they have no sort of weird 3D conformation. They're going to be the same compounds, guys, okay? If you get 1, all you need to do is identify R and S, okay, on both compounds and just compare them. Are they both R? Are they both S? They're identical molecules, okay? If one is S and one is R, however, they will be enantiomers, okay? All right. This is where it gets more complex, okay? So, if I have 2 or more chiral centers and it works for like however many that you have, as long as there's 2 or more, you're just gonna need to label every single one R and S, okay? If let's say on the first compound they're all R, and on the second they're all R, then they're identical, okay? But let's say I have 3 chiral centers on each I have 3 chiral centers on each one, and let's say 2 of them are the same, but one's different, okay? So as I'm going through, I have R, R, S on the compound on the left, and on the compound to the right, I have R, S, R or something, okay? R, R, S, and then R, S, R, that works. Some of the chiral centers are different, but not all of them. Therefore, it's a diastereomer, okay? All right, now that brings us to the last 2. If I'm going through and I'm labeling and I have perfectly opposite, so I have SS on my compound to the left and then RR to the one on the right, then they might be enantiomers unless I can draw a plane of symmetry through them, making them meso and identical. Okay. Okay. Practice time. Don't do A. Start with B. Okay. What'd you guys get for B? All right. I'm gonna wait for a few more answers. What? No. Okay. All right. Yeah, I think that's it. Yeah. All right. Yeah. Good job. Do you see? All right. Let me know when you guys are done with C. Okay. So the majority of you guys were right. it is going to be a constitutional isomer, okay? Now, someone in the chat asked a good question. Why would they not be considered constitutional isomers? In order to be a constitutional isomer, one of these either carbon-carbon bonds or carbon-oxygen bonds would have needed to have changed position relative to the others, okay? That's not what I want. Okay, so all right, right now, what do you guys see? Do you see the PowerPoint or do you see the whiteboard? Okay. We didn't answer A. Okay.
Oh, sorry. Quick question.
Yeah, go ahead.
Did you say C was a constitutional isomer or a diastereomer?
Diastereomer.
Okay, awesome. Thank you.
All right, so I'm going to work the two out, okay? I'm going to work out B and C. And for those of you who are curious, yes, I believe A is going to be a diastereomer. It's a type of geometric isomer, but we really don't care in this class. Okay. OH. Okay. So everybody can see the whiteboard, right? Got it. Okay. So we're going to start off with blue. All right. Oxygen's number 1. This carbon over here is going to be number 2 because it is connected to a fluorine, a carbon, and a hydrogen. Whereas this one is connected to a hydrogen, a hydrogen, a hydrogen. And fluorine is has a higher atomic number than hydrogen. Therefore, the fluorine is going to take priority over the methyl. Okay. And then the H is behind. So the fourth group is behind. Okay. So I'm going to connect 1 to 2, 2 to 3, 3 to 1. That is S. Okay. Give me a second. Zoom's being difficult. Okay. On this carbon, fluorine is going to take 1. This carbon over here is going to take 2. That carbon is going to take 3. Okay, I'm going to go 1 to 2, 2 to 3, 3 to 1. That is also going to be S. However, H is in the front, so it's going to be R. Okay. Now, technically, what I should have done as my first step is look at the molecular formula and the connectivity of the two compounds I gave. But they're both the same, so I kind of just skipped it. But on the test, I want you guys being more careful, okay? Because that is a question that would kind of suck to get wrong. You know what I mean? All right. So when I'm looking at this, right, I see that the OH is the exact opposite as it is on the left side. Okay, so this and this are like exactly opposite, okay? One's on a bold wedge, one's on a dash wedge. So it's not really that hard for me to say, okay, this is going to be R. But I'm going to double check just in case. 1, 2, 3, 1 to 2, 2 to 3, 3 to 1. That looks like S, but H is in front, so it's R. Okay. All right. On the other compound, on the other chiral center. Fluorine 1. Over here is 2. This is 3. 1 to 2, 2 to 3, 3 to 1. That is going to be S. Okay. So we have two chiral centers that are both the opposite of one another. Therefore, they're going to be enantiomers. Okay. Does that make sense? Where you can find a recording of this, hopefully YouTube. But for some reason, computers don't like me. So we'll see. Okay, hopefully I can get everything like recorded and then uploaded, but like I can't guarantee it. Okay. All right. Okay. Oh, I completely skipped that. Stop share again, and then I'm going to work through the other one real quick. All right, so this here and this here are the exact same. Okay, so I don't really need to check them. I mean, if I have extra time on test day, you could, but they're literally the exact same thing. They're not going to differ. If one's R, the others are. If one's S, the other is S. Here, same thing again. Okay. And then finally, this one, and give me 1 second. Let me change the color. This one here and this one here, those two are going to be different, right? Because basically, if this one over here on the left side is going to be a dashed wedge and this one's over here on the dashed, then it's going to result in a change in stereochemistry. And I'll show you guys how that plays out. All right. So let's start at the top here. 1, 1, 2, 2, 3, 3. 1 to 2, 2 to 3, 3 to 1. That's S, but it needs to be flipped to R, okay? Why is the wedge second? Okay. So I want to compare that carbon and that carbon. Okay. Let's see what they're connected to. This top one is connected to a carbon, a hydrogen, and a hydrogen. And then the one over there is connected to a carbon, and a hydrogen. Okay. This second atom gives us that first point of difference, which tells us then, okay, carbon is heavier. I'm sorry, has a higher atomic number than hydrogen. Therefore, that's going to take priority. Okay. Make sense? Awesome. All right. Next one. So looking at this carbon and this carbon, okay, this top is going to be 1, okay, this bottom one's going to be 2, and the methyl is going to be 3. Okay. 1 to 2, 2 to 3, 3 to 1. Okay, that's going to be R. Okay. Alrighty then. Last one to look at. If we go through this, that's the carbon I want to look at. This is going to be 3. This is going to be 1. Just give me 1 second. I'm going to change color. This here is going to be 1, followed by 2 and 3. Okay. 1, 2, 3. All right. 1 to 2, 2 to 3, 3 to 1. 1 to 2, 2 to 3, 3 to 1. All right. Those both look like R. However, over here, I have my 4 group in front. Therefore, I need to flip this one. So this is actually going to be S. This is going to be R. Okay. Therefore, there is one difference between the stereocenters. So it's a diastereomer. Everyone follow? Nice. Okay. This slide basically just says like, hey, this is the definition of this. This is the definition of this. Does Dr. Dowdy still have that little definition section on each test?
He didn't have any on the last one, I don't think.
Okay. He might not have any on this one. But like if he did, it'd be this. It's a good thing you're here. Someone just asked in the chat how to tell if it's a miso. If I don't cover it by the end of the PowerPoint, yell at me and I'll go back and I'll teach you how. Okay. This slide is more the same as it was last slide. It is just, hey, Here's the definition of this. Here's the definition of that. One thing I do want to actually like kind of harp on a little bit, and this is kind of more for biochem than it is for orgo, but DNL has nothing to do with RNS. Nothing. Okay. RNS is absolute configuration. DNL is more relative. Okay. Okay. Really? Huh. Okay. So here, determining chirality. Chirality. This is the answer to the meso question in chat, okay? It's actually pretty simple. All you need to do is look for a plane of symmetry. Okay, a plane, not an axis. Take A, for example. I can draw a plane straight through the middle, right? On both sides, it's the exact same, right? Therefore, this is a meso. Therefore, this is achiral. Okay? Let's take compound B. Is that a plane of symmetry? Yes or no? Great. Therefore, this is not a meso compound. Therefore, as long as there are chiral centers, it's chiral. Okay? Does that help? Perfect, perfect, perfect. Yeah, I don't know why my slides ended. Because there is way more. All right. I just have to go for memory. All right. Give me a second. All right, so we are going to start with let's see, we should probably start with rotation. Let me pull up my textbook really quick. Okay. Oh no, we're almost done. Yeah, we have like Fishers and E and Z, and then we're pretty much done. Okay, awesome. All right, so very first thing, what is a Fisher projection? Okay, 1 second. Somebody in chat just asked a question that I think I understand. Yes. Yes, if it basically if you have two chiral centers and they're both not the same. Basically, just use the plane of symmetry test and you're gonna be fine. Okay. There is one other example that's really kind of messed up. I'm gonna draw you guys something. See this? Can you guys draw a plane of symmetry? So this is not a meso, right? All right, I'm about to blow your minds. This can be changed. Okay. Come on. Into this. Can you draw a plane of symmetry through that? Yeah, it's a meso. Does that suck? Yeah. But you're gonna need to know it, okay? So I really essentially what I want you to do is just commit this to memory, because like even I wouldn't catch this. Yes, it is. It is. Okay. Oh my God. Work. You know, I should have listened to people when they said get an iPad. And now it works. Yep, cyclic compounds don't really allow for single bond rotation. Right. So therefore, this is not something that you're gonna need to check for. And honestly, guys, like I would really only do this if it's like that obvious. Otherwise, I just wouldn't recommend caring. Okay. This makes sense. Awesome. Okay. Awesome. Good. All right. Now we're gonna get into Fisher projections. So the deal is, what are Fisher projections? Fisher projections are kind of just a cleaner way to show, well, actually, they're in like the real world. I've only really ever seen like fissures drawn in for like sugars, because like they just kind of make them look a bit cleaner. They also make it really easy to convert between different sugar forms. And so therefore today, I'm literally just gonna go over what sugars look like in fissures and apply it. Okay. Six. All right. So this sugar is a D-glucose. For those of you who are taking your MCAT, you are going to be expected to memorize that structure, okay? But for our purposes for this class, we do not. But we are going to need to be able to convert between this Fisher given and bond line, and then bond line back, okay? So I'm going to show you guys a little trick. So first step that I want you guys to do is number it, okay? 1 through 6, okay? Then you're going to take that You're going to draw the carbon skeleton of the structure out by using the carbons that you have counted. Okay. All right, so that's the first step. The first step is to just number it. The second step is going to be to draw out the carbon skeleton, okay? All right. Next thing that you're going to actually be doing is each one of these points is a chiral center that is going to look like this. All right. So keep that in mind when we get to R and S. So OH is 1, this carbon is 2, this is 3, 1 to 2, 2 to 3, 3 to 1. That's S, but I need to flip it to R. Okay. This is OH. This is 2. This is 3. Okay, yeah, no. One second to clean this up. Okay. This is 1. Up here is 2. Down here is 3. 1 to 2, 2 to 3, 3 to 1. That looks like R, but I need to flip it and it's S. Okay. Now I stop. I start cleaning it up. Okay. This is 1. This is 2. This is 3. 1 to 2, 2 to 3, 3 to 1. That is going to be look like S, but then we're going to flip it to R. I skipped one. One, 2, 3, 1 to 2, 2 to 3, 3 to 1. That is going to look like S, and then I'm going to flip it to R. Okay, so R, S, R, R. Those are the conformations at carbon 2, 3, 4, and then 5. All right, so what I'm going to do is I'm going to go over right on my carbon skeleton, R, S, R, and R. Okay, that's going to make this next step a lot easier. So the next step is just by random choose bold wedge or dashed and say, okay, let me check the configuration, see if this matches what I need it to be. Okay, so 1, 2, 3. That is going to be S, right? I don't want that. I just had a question in chat. The third one is R because the OH is number 1. The carbon above it is 2. The carbon below it is 3. Okay, so it's going to be like 1, 2, 3. Right, it is going to be S, and then I flip it to R, right, because the H is in front. Does that make sense? I know the H is in front because of this. Right, because H is on the side, I know that's going to be in the front. And I know that in every time that I have that H on the side, it's always in front, so I always need to flip. Okay. Okay. Awesome. So back to here, 1 to 2, 2 to 3, 3 to 1. That's S. I don't flip it, but that's not what I want because I want R, right? So all I have to do to make my structure reflect what I want is erase that bold bond, make it a dashed. Not in that color though. All right. And now that's the right one, right? I want it to be R. It is R. So I move on to the next carbon, okay? I say, okay, I think it's going to be like that. All right. So I go, I say 1, 2, 3, 1 to 2, 2 to 3, 3 to 1. That is R, but I want S. So what I do is just flip whatever I have to being a dashed wedge. There we go. There. All right. Everything makes sense so far? You're just going to rinse and repeat this step until you get to carbon 5, okay? Carbon 4 is R, all right? I think it's going to be that. All right, now I'm going to see if I'm right. 1, actually, let me redo that, pick a different color. 1, 2, 3, 1 to 2, 2 to 3, 3 to 1. All right, that is S, but because H is in front, I need to flip it to R, and so I am right. I can move on. No need to flip it if you already have the configuration correct. All right, last one. I think that it is going to be this. All right. 1, 2, 3, 1 to 2, 2 to 3, 3 to 1, and that is R. And I am done. So my final structure is just what is in black. All right. Does this method make sense to everyone? Okay. I know it takes a while. That's okay. It will always get you the right answer. Yes, you have to flip the configuration that you get because H is in front.
Oh, quick question.
Go ahead.
You mind going over how carbon, what is it? 1, 2, 3. How carbon 4 is R
Yeah. On which structure?
on the Fisher projection?
Okay. Okay, there we go. 1, 2, 3, 4. I'm gonna clean it up a little bit. I hope so. I hope so. I can't guarantee that. But I hope so. If there is, it will likely be on YouTube. I'm going to try to use my best computer that I have in order to upload it, and I'm hoping it will go faster because of it. But again, there's no guarantee. Right, so OH is 1. I can try joining the GroupMe, and then I'll just post it there. Just let you guys know about it there, that is. So around this carbon, right? 1, 2, 3, 4. This oxygen is 1. Above it is 2. Below it is 3. 1 to 2, 2 to 3, 3 to 1. That is S, and then you flip it to R. Okay?
Okay, thank you.
Awesome. That's a really good question. It has to do with kind of the way things play out, right? So I get that question a lot. So I'm looking at that carbon, seeing if it's a chiral center. If we go above, right, on that boxed, these two boxed, I have a hydrogen and oxygen. A carbon and an oxygen. It's on here. For here, I have a carbon, a oxygen, and a hydrogen. Okay. Then I go up again to here and here, right? And I have a carbon, an oxygen, and a hydrogen. And then down here in the green one, the bottom one that's circled, I have an oxygen, a carbon, and a hydrogen. So I have another tie. And then I go again to that brown here and here. So the top one's going to be oxygen, oxygen, hydrogen. The bottom one is going to be oxygen, hydrogen, hydrogen, right? So that top one has 2 oxygen bonds and therefore it wins. Make sense? Nice. Awesome. Yeah, I know it can be really hard to kind of track that all the way through. What do you mean for 1? Okay. If that's the carbon I'm looking at, I'm sorry. 1, 2, 3. 1 to 2, 2 to 3, 3 to 1. That is S, but H is in front, right? So I need to flip it to R. Does that clarify that?
Um, oh, can you hear me?
I can hear you.
Oh, okay, sorry. So for number 2, for 2 and 3, they're oxygen and oxygen. Oh,
Okay.
it's
The rule,
OOH.
you have a double bond to
Oh,
carbon to
okay.
oxygen, therefore you count that as 2 different bonds.
Okay. Okay. That's all. You answered my question.
Awesome. Good. Okay. Anything else before we move on? Okay. So, last thing before we move on, all right? So, is this E or Z? That is the question. Okay. What you're going to do is you're going to take a line, you're going to draw it perpendicular to the alkene. Okay. Then you are going to number the substituents on each side using the same rules that we were just using. Okay. Once you do that, you're going to take another line, you're going to draw it parallel. And then you are going to say, okay, where is number one to each other? Are they on the same side of the blue line or an opposite? Okay. If they are on the same side of that blue line, they are going to be Z. If they are on opposite sides of the blue line, they are going to be E. Okay. Makes sense. Awesome. That's chapter 7. I'm sorry, that's chapter 5. Z is the same side. Everything makes sense? Okay. Let's take like a 5-minute break, okay? Okay. E is going to be opposite sides of the alkene. Z is going to be the same side. Oh, shoot. All right. Do you get it? Awesome. Okay. All right. Let's continue on to the next chapter in like 5 minutes, okay?